Welcome back. So in this lesson, we are going to talk about the relay settings, how we come about making those settings. In the very first part of this, we are going to be looking again at our IDMT relay and its principle on our plug setting. So looking back into that diagram that we had, if that plug had to be removed from the plug bridge, then our contact would close on these relays, ensuring your least sensitive setting of your relay was selected, which would be the one at 200%. And that is why we say that 200% position gets utilized for us to calculate our CT ratio, because it ensures that we never have an open circuit scenario on our secondary winding of our relay. The 50% position is utilized to calculate what we call your CT's burden, or your total resistance of your relay connected to the CT. So the operating time of the relay depends upon how long a distance to be traveled by the moving parts of the relay for closing the relay, and this we call the TMS, time multiplier setting. It also depends on how fast the moving parts of the relay cover the distance, which is our PSM, plug setting multiplier. So our relay distances usually are from 0.1 to 1. Then we have what we call our 0.1 is the shortest traveling distance, and 1 is the longest traveling distance. So when you work out your TMS, you're really wanting to get values between 0.1 and 1. What do you do when you get a value below 0.1? Then you must take your first value as 0.1, because that's what we need to work in. Once you get it to be over 1, you must know that there is really something wrong with our circuit, and you need to choose a different type of relay to utilize. I'm now going to introduce what we call your setting current IS. And what this setting current, what we want from it is that is the current the relay needs to operate at. But it needs to be higher than your maximum load current that you have on your circuit, and it also needs to be higher than what you call your overload system that you have on your current, so that this relay does not really cater for an overload scenario, because we know for transformers we usually can allow overload of up to a certain amount of time. So how do we then do the application of this overcurrent protection in practice? The operating current of the relay is the current necessary to start the disk rotating. Okay, and then the operating current is slightly higher than what we call our IS, which is our setting current. So we have minimal standard that is saying at 110% of our setting current will be our operating current. And then it says that 90% of our setting current will have our resetting current value. And then for induction motor loads, it says that your starting current of your largest motor should be considered when making our relay settings. And why is that? Because we know that our starting current for motors is much higher than our normal circuits, or our normal operating currents for our motors. It can go up to 6 times of that. So when we do a setting for motors protection, we must make sure that we are not going to trip our circuit looking at your starting current. Then we come now to the principle of the system, where we are saying we are coordinating. And what is this coordinating really going to be involved in? So in this, we say we need the certain data that we require for our relay study to be done. The first thing is you either need to have a single line diagram of your power system, or you need to have a description of what is happening exactly in your power system. So you need to know where is your source, how far is it, how big is it. Then you need to know your distances between all of your other substations, and you must know if there is any transformers in those substations or not. Then the second one is you need to know your impedances in ohms. In other words, that distance gets translated into your impedance. Now, all of your wires or your conductors and your cables, they usually have impedance that they are provided with by the manufacturers. And all you need to do is to multiply that by your distance of their points from a certain point A to a certain point B. You also need to know the impedances of all of your transformers or your rotating machines and feeder circuits. And usually these will transform into per unit system. Then you've got your maximum and your minimum values of your short circuit current that are expected to flow through each of these protection devices so that we can start our settings from those various points. Then we've got our maximum load current through the protection devices. We also need to have what our starting current requirements are for motors, and we need the transformer inrush currents and the thermal withstand. Thermal withstand means that how much overloading that system can be able to take. We now need also the decrement curves showing the rate of decay of our fault current supplied by our generators so that we know exactly then what is the current faults that those generators can be able to take. Then we have our performance curves of our CTs so that we know if there are any errors that we need to be able to compensate for. The basic rules are generally stated such that whenever possible, we need to use the relays to have the same operating characteristic in series with each other. Now, in our IDMT relays, we have got three types of relays. You've got a standard, you've got an extreme, and you've got a very extreme. So you need to be sure that if you are choosing a standard, then all of them need to be standard relays. If you are choosing an extreme, they need to be all the same characteristic. That's what that line is saying. Then we also need to make sure that the relay furthest from our source, that means the relay closest to wherever the load point is on your system, has current settings equal or less than the relays that are behind it. So it must either be equal to the relays behind it or it needs to be less than those in their current settings. And this is so that the primary current required to operate the relay in front is always equal or less than the primary current required to operate the relay behind it. And now let's listen to why is this the case. Remember, we're working on a impedance scenario. So in other words, at bus E, which is my last bus to closest to the load, my current really cannot be more than the one at bus D. It can either be the same because the impedance is the same, or it can be less, okay? Because our impedance at E, we expect it to be more. Why? Because it's got the longest distance on your system. So that is what this scenario is saying. We are now looking at our multiple offsetting current, which we either call M or sometimes we call it our PSM. So a multiple offsetting current is going to be IR in this scenario, and that we say is our secondary current divided by our setting current. And our setting current, we say it is our nominal current, which is our normal load current, multiplied by our plug setting. Then we say our secondary current is really your primary current divided by your turns ratio of your CT. And our IR again, which is our multiple offsetting current, we can look at it as having a combination of what is above, and we say it becomes our fault current, and we can divide that by our turns ratio of our CT multiplied by the plug setting. And what is the turns ratio of your CT is really your primary over your secondary of your ratio. So the first thing that we look at here is our pickup current of your relay. And this pickup current is the current which your relay initiates its operation, which is gets calculated by saying your overload rating of your system divided by your primary current of your CT times your secondary current of your CT. This can also be just written as your overload rating divided by your turns ratio of your CT. Then we have what we call our plug setting, PS. So our plug setting, which is also known as our current setting, our IS guys, is then your position is selected on that plug bridge, which means that that position between 50 and 200% or 1 to 5. And that becomes our pickup current divided by your rated secondary current of our CTs times the 100% because it must be in percentage form. Or if you did not go and calculate the plug pickup current, you can go straight to your plug setting, and really what it will be your overload rating. Then you will divide it by your rated primary current of your CT, because then your rated secondaries will just be cancelling out, and you'll multiply that by 100%. So all that your PS is that pickup current without your secondary current involved in the calculation. Then we have our plug setting multiplier, which is your ratio of your fault current in the relay to the pickup current of your relay. And this will determine the actual time of operation for your particular relay. So this is your IR, and we are going to say it will be your fault current that you have on your system divided by your pickup current. Again, if you didn't do what your pickup current is, it means that is that fault current divided by what you will then have as your plug setting multiplied by your rated CT primary current. Okay, then we go on and we look at our time setting multiplier, which is our TSM. And this is our operation time of our electrical relay. And the combination of the distance traveled by the moving parts of that closing for the relay contacts. Then we have what we call our time grading margin, which is the time interval that we allow between two relays that are adjacent for their operation in order to achieve what we call our discrimination between them. And that total time you see in red that says is equal to relay time plus grading. I want you to keep that for now. You will see when we start doing things in the practice how it comes across. So I've started out by putting very simple examples just so that we can get the easy principles to go by, where you have a scenario of an overload or an overcurrent relay with a nominal current of 5 amps and it has a plug setting of 75%. And they say calculate the setting current of that relay. So our setting current would then be equal to that nominal multiplied by that plug setting, which would be in this case the 3.75. Okay. Then in this scenario, they say you've got an overcurrent relay with a nominal current of 1 amp now. So our CTs, as we had defined before, remember that it can either be a 1 amp or a 5 amp on the primary side. So the previous one was a 5 amp, this one is a 1 amp. and has a plug set of 175%. Calculate the setting current of that relay. So our setting current again would be the 1, and I multiply it by the 1.75, and I get 1.75 amps. So what is noted at the bottom is that the primary current in a power system is known. Then your current in the secondary of your CT must be calculated by taking that ratio of your CT into account. Then on example 3, we go in a little bit more now so that we can even go up to our IR in calculations. It says that we've got a fault current in a system that is 4,150 amps. A current transformer with a ratio of 500:5 is connected to an overcurrent relay with a nominal current of 5 amps and a plug setting of 125%. And they say calculate the multiple of setting current with the fault current flowing in the system. So we start by saying, okay, what is our I secondary going to be? It is going to be our IP, which is really our fault current, divided by our turns ratio, which is then really the divided by 500/5. And therefore that says times 5 divided by 500. You will get your 41.5 amps. We then take that 41.5 amps, we put it into a formula for IR, and then I divide by my IN, which is the 5, multiplied by my plug setting, which is the 1.25. And I can then get my 6.64. Then we have another example, and they say a fault current in a system is 4,000 amps. An overcurrent relay with a nominal current of 1 amp and a plug setting of 50% is connected to a 800:1 CT. Again, I go and work out what my IS is going to be. I get 5 amps. I go and put that in there, and I'm able to calculate what my IR is going to be.